Hello everyone, and welcome back to my new video. If you've ever trained an SVM model, you've probably come across parameters like C, gamma, and different kernel functions. But what do these parameters actually do? How do they affect the decision boundary? And how do you choose the right values? In this video, we'll answer these questions step by step. We'll first develop an intuitive understanding of how support vector machines work and why they're considered one of the most powerful algorithms for classification. Then we'll explore the key hyperparameters that many tutorials only mention briefly, including C, gamma, and the different kernel functions. We'll also discuss how to select the right kernel and use techniques like grid search to find the optimal configuration for your model. By the end, you'll know how to optimize SVM for your own data. Let's get started.
Before we get started, I'd like to introduce a brand new segment that will be part of every video from now on. At the beginning of each video, I'll ask you a machine learning challenge. Your mission is simple. Watch the video carefully, apply what you've learned, and see if you can solve the challenge by the end. Then, don't forget to leave your answer in the comments. Let's see how many of you can get it right. So, here's today's challenge. The image on the left and the image on the right were both generated using an SVM with an RBF kernel. Only the values of C and gamma were changed. Which combination of hyperparameters transformed decision boundary 1 into decision boundary 2? Keep these options in mind while watching the video. By the end, you'll have everything you need to figure out the correct answer. Imagine there are hundreds of possible decision boundaries. SVM doesn't choose a random one. Instead, it finds the boundary with the largest possible margin. Why? Because larger margins usually lead to better generalization on unseen data. The data points that determine this boundary are called support vectors. Notice that most of the remaining data points don't actually affect the model. When people learn about support vector machines, or SVM, they usually focus on this solid line in the middle. We call it the decision boundary, or the separating hypoplane. Its math formula looks like this, where W is the weight vector, X is your data, and B is the bias. Anything above it is predicted as class 1, and anything below it is class 0. But here's the secret. This line actually has no independent power. It is entirely controlled by something else, these two dashed lines on the sides. These dashed lines are the margin boundaries. Think of them as the shoulders of a highway or a safety buffer zone. SVM enforces a strict rule. Every data point must stay behind its own margin. For the positive class, the boundary is. And for the negative class, it is. Using vector geometry, the total width of this highway, the distance between these two dashed lines is mathematically proven to be 2 over the norm of W. Ultimate goal in SVM is to make this highway as wide as possible to ensure maximum safety for future data. But what happens when data is messy and points leak into this safety zone? That's where zeta, or the slack variable, comes in. Zeta is actually the distance from a point to its own class's dashed line. It measures the crime of trespassing. If a point is safely outside the dashed line, zeta is 0. If it crosses the dashed line but stays on its correct side of the highway, zeta will be between 0 and 1. And finally, if it crosses the middle line entirely and lands in the enemy territory, zeta will be greater than 1. This is a flat-out misclassification. If we want to have the widest margin, we should minimize this term, the norm of W, and this brings us to the core math of SVM. The cost function is actually solving a beautiful tug-of-war between two rival forces. On one side, we have 1/2 norm of W squared. Because it wants to minimize norm of W, its entire life goal is to pull the rope and widen the dashed lines as much as possible. On the other side, we have the sum of all zetas. This team wants to pull the rope to minimize errors, demanding that no data point ever enters the highway. They are locked in a fierce battle. So who decides the winner? The referee of this match is parameter C. C is the penalty weight, and you have total control over it. If you set C to be very small, the referee ignores the errors. The margin maximizer wins the tug-of-war, pulling the rope to create very wide dashed lines, allowing points to cross freely for the sake of a wider highway. But if you turn C way up, the referee becomes incredibly strict. Any tiny error is multiplied by a massive C, destroying the score. The error penalizer team wins, forcing the dashed lines to shrink and become extremely narrow. A large value of C forces the model to classify almost every training sample correctly. This often creates a more complicated decision boundary. A small value of C allows a few mistakes in exchange for a wider margin. As a result, the model often generalizes better dots. So remember this simple rule. Large C means low bias, but higher risk of overfitting. Small c means higher bias, but better regularization. We saw how SVM uses a straight line to separate data, but look at this dataset. The red points are trapped in the center, and the purple points are surrounding them. No matter how you draw a straight line in this 2D space, it is impossible to separate them. This is where we need a magical tool called a kernel. A kernel is essentially a shortcut function. Instead of struggling in 2-dimension, it applies formulas like these to compute a new higher dimension, in this case, a 3-dimensional z-axis. As you can see on this interactive 3D plot, by lifting the data into the 3rd dimension, the red points sink down and the purple points shoot up. Now, a flat 2D plane can easily cut through the space and separate them perfectly. In our example, we only added one extra dimension, and suddenly a flat hyperplane could separate the data perfectly. But in real-world machine learning, things are very different. Our datasets rarely have just 2 features. They may contain 20, 50, or even hundreds of features. Now let's imagine that instead of 2 input features, our dataset contains 20 features. If we decide to use a second-degree polynomial transformation, we don't simply double the number of features. The reason is that the transformation must generate every possible polynomial term up to degree 2. First, we keep all of the original features. That's 20 first-order terms. Then we generate all squared terms. That's another 20 features. We must also include every pairwise interaction between the features. The number of these interaction terms is 190. So the total number of generated features becomes 20 plus 20 plus 190 equals 230. And this is only for a second-degree polynomial. Now imagine increasing the degree to 3. In addition to all of those previous features, we would now need to generate every possible third-order interaction.
Total features explode to 1,1770.
Creating tens of thousands of features is both memory-intensive and computationally expensive. Fortunately, support vector machines have a beautiful mathematical shortcut. This shortcut is known as the kernel trick. Earlier in this video, we introduced the SVM optimization problem in its primal form. Solving that problem directly would require us to explicitly compute all of those transformed features. Instead, SVM converts the optimization problem into another mathematically equivalent form called the dual optimization problem. We won't cover that derivation here, because it involves Lagrange multipliers and constrained optimization. The important thing is this. After this transformation, SVL no longer needs the transformed features themselves. It only needs the dot products between them.
But what if our decision boundary cannot be described well by any low-degree polynomial? In that case, we need a completely different way of measuring similarity. That's exactly where the RBF kernel comes in.
For RBF kernel, instead of creating polynomial combinations, the RBF kernel compares every pair of training samples based on their Euclidean distance. After measuring the distance between 2 samples, the RBF kernel converts that distance into a similarity score between 0 and 1. The closer the samples are, the closer the score is to 1. The farther apart they are, the closer it gets to 0. The gamma parameter controls how quickly this similarity decreases with distance. Suppose we have 100 training samples. The RBF kernel computes the similarity between every pair of samples. These similarity values are stored in a 100 times 100 matrix called the kernel matrix. Each element of this matrix tells us how similar one training sample is to another. Notice that we're no longer working with the original coordinates of the samples. Instead, we're working with their pairwise similarities. Now let's look at how the RBF kernel actually works. We start with our original data in the input space. In this example, the data has 2 features, so we can visualize it in 2 dimensions. The first step is to calculate the Euclidean distance between every pair of training samples. So if we have 100 samples, we obtain a 100 by 100 distance matrix. Each value in this matrix tells us how far one sample is from another. But distance itself is not yet a similarity measure. That's why the RBF kernel transforms each distance using the Gaussian function. Samples that are very close to each other receive similarity values close to 1, while samples that are far apart receive values close to 0. These pairwise similarities form the kernel matrix. You can think of each row of this matrix as a new representation of one training sample. Instead of describing a sample only by its original coordinates, we now describe it by how similar it is to every other training sample. This creates a much richer feature space. In that new space, SVM still does exactly what it always does. It searches for a linear hyperplane. The hyperplane itself is not curved, but when its effect is viewed back in the original input space, it appears as a nonlinear decision boundary. Now let's look at the role of gamma. Gamma controls how quickly similarity decreases as distance increases. With a small gamma, each Gaussian function is wide. That means even relatively distant samples can still influence each other, creating a smoother decision boundary. With a large gamma, each Gaussian becomes narrow and sharp. Similarity then drops very quickly, so each sample mainly affects a very small neighborhood around itself. This gives the model enough flexibility to create highly detailed and irregular boundaries. That flexibility can be useful. But if gamma is too large, especially when C is also large, the model may start fitting noise in individual training samples, instead of learning the general pattern. So in practice, C and gamma should usually be tuned together using cross-validation. Now let's see the combined effect of changing C and gamma simultaneously in this video. Look at the top left chart. Here, both C and gamma are low. The model is incredibly relaxed. See how the decision boundary is a simple, smooth, and gentle curve? It's ignoring some of the noise and focusing on the big picture. Now, shift to the top right. We cranked C way up. Remember, C is the referee. By increasing it, the model becomes strict. It's forcing the margin to squeeze tight to get every point on the correct side of the boundary. Even though the boundary is still smooth because gamma is low, the model is working much harder to minimize those errors. Down here on the bottom left, we have low C but high gamma. This is a weird contrast. Gamma is trying to create sharp, localized pockets around individual points, but because C is low, the model is still forgiving. You see the boundary starting to wiggle and bend, but it's not yet committing to perfectly capturing every single outlier. Finally, look at the bottom right. High C and high gamma. This is the danger zone. The model is both aggressive and obsessive. It is creating tiny, isolated islands and sharp, jagged edges around every single point. It's not learning the pattern anymore. It's memorizing the noise. This, my friends, is a textbook case of overfitting. A large gamma doesn't directly cause overfitting. It makes every training sample influential only within a very small neighborhood. If we also force the model to classify every training sample correctly using a large value of C, the decision boundary becomes extremely complex, leading to overfitting.
Now it's time for today's challenge. Based on everything we've covered in this video, which option do you think is correct? Leave your answer in the comments using only A, B, C, or D. I'll be reading your comments and replying to as many of you as I can. Good luck, and I'll see you in the comments. Thank you so much for watching this video. Today, we went far beyond the basic idea of support vector machines. We learned how the parameter C controls the trade-off between maximizing the margin and minimizing classification errors. We explored why a simple linear hyperplane isn't always enough, and how transforming the data into a higher dimensional feature space allows SVM to solve much more complex classification problems. We discussed the differences between the linear, polynomial, and RBF kernels, and more importantly, when each of them is the right choice for a real-world problem. We also saw how the kernel trick makes these powerful transformations computationally practical, without explicitly constructing thousands or even infinitely many new features. Finally, we learned how the gamma parameter controls the influence of each training sample, and why C and gamma should almost always be tuned together using cross-validation to build a model that generalizes well instead of simply memorizing the training data. Remember, choosing the right kernel isn't about memorizing rules. It's about understanding your data, understanding the relationships hidden inside it, and selecting the model that best captures those relationships. If you found it helpful, please support the channel by liking this video, subscribing, and turning on the notification bell. It really helps me create more high-quality machine learning content like this. Until then, keep learning, keep building, and I'll see you in the next video.